In the previous video on Aharonov-Bohm effect, we have seen that if in the case of double slit experiment with charged particles, we put a solenoid between two slits P and Q, then the interference pattern that we get is displaced. And we also calculated the probability for a charged particle to be at a point n on the screen, and we found that this probability was proportional to 1 plus cos of phi, where phi was the phase difference between paths m, q, n and mpn. We calculated this phase difference and we found that there were two contributions to it. First contribution was due to the kinetic energy term in the Lagrangian, and this was equal to 2 pi times L2 minus L1, where L2 is the length of path MQN and L1 is the length of path MPN, divided by h bar. Sorry, not h bar, but lambda dB. Lambda dB, where lambda dB is de Broglie wavelength corresponding to the particle, which is h divided by mv. So this was a contribution due to the kinetic energy term in the Lagrangian, and the other contribution was due to this v dot a term in the Lagrangian, q times v dot a term, and this contribution we calculated it was equal to q times f divided by h bar. This was a contribution due to q times v dot a term in the Lagrangian, and f was equal to integration of path integral of a along the path m, q, n, p, m. This loop m, q, n, p, m. So this was the definition of f. In the previous video, we related f to the flux passing through this loop m, q, n, p, m by using Stokes' theorem. We argued that if we use Stokes' theorem, then this is integral of curl of A through this area bounded by this curve m, q, n, p, m, and since curl of A is equal to B, so integral of B through this bounded area was equal to flux. This is what we did in the previous video. So in that case, A dot dl, this integral, this path integral, was coming out to be equal to the flux through this loop. Now suppose we replace this solenoid, we remove this solenoid, we have removed the solenoid, and instead of this solenoid, suppose we place a magnetic monopole below this setup. So far below this setup, we are putting a magnetic monopole, and suppose the charge of this magnetic monopole is G. This is placed somewhere far away below these two slits, and the charge of this magnetic monopole is G, so that it produces a magnetic field mu naught by 4 pi G over R square. This is the magnitude of the magnetic field that it produces, and it is a radial magnetic field because it is a monopole. So this is the magnetic field that this monopole produces. So we are assuming now that we have a monopole. So with this monopole as the center, suppose this is at a distance R from this setup, below this setup. This distance is R. So we draw a sphere of radius R with center at G, this monopole. So we consider a large sphere. We consider a large sphere, and we assume that this sphere is so large that this curve M, Q, N, P, M, this lies on the surface of this sphere. So we consider that this is a very large sphere of some radius R. This monopole is placed at a large distance from this setup, below this setup, so that this curve M, Q, N, P, M, this fits on the surface of this sphere. Now, in case of such a monopole, we will have a magnetic field, and we'll have a vector field A, which vector potential A, which will appear in the Lagrangian of the particle, and the phase shift, the contribution to the phase shift coming from this vector potential will still be given by this expression qf by h bar, where f is the integral of A, path integral of A along this loop M, Q, N, P, M. However, this path integral now does not give a unique answer. If we apply Stokes' theorem, then there are two different surfaces that we may consider, where we may take the integral of curl of A. First is the surface which is inside of this loop M, Q, N, P, M. Let us call this surface S1 or S. Suppose we call this surface S, which is inner to the loop M, Q, N, P, M, and we call S prime to the outer surface to the loop M, Q, N, P, M. This surface will have a negative orientation, and both these surfaces S and S prime have this M, Q, N, P, M as their boundary. So both S is this surface. This is the surface S, which is bounded by M, Q, N, P, M, which is the inner surface, and the outer surface bounded by this loop M, Q, N, P, M is this outer surface. this part of the sphere. So these are the two surfaces, and both of these surfaces have this loop M, Q and PM as its boundary. For the outer surface, the orientation will be reversed, and for the inner surface, orientation will be perpendicular, outward perpendicular to the sphere. And for the inner surface, this orientation will be outward perpendicular to the sphere, and for the outer surface S prime, its orientation will be perpendicular inwards to the sphere. So if we consider Stokes theorem using S, if we consider Stokes theorem with the surface S, then with this definition, F corresponding to surface S will be this A dot dl M, Q and PM. If we calculate F corresponding to S, then this will be curl of A dot ds over the surface S, and this will be flux through S. But this monopole is producing a magnetic field which is of the form mu naught upon 4 pi G by R square. This is the magnitude of the magnetic field which is being produced by this monopole. So the flux passing through this inner surface S will be simply proportional to the area of this inner surface. So this will be magnetic field. Magnetic field is constant at S, mu naught upon 4 pi G R square, and if omega is the angle subtended on this surface S, omega is the angle subtended on this surface S, and R is the distance, then this is the area of this surface S, omega times R square. So area multiplied by the magnitude of the magnetic field will be the flux through S, and this will be equal to mu naught times G times omega divided by 4 pi. So this is our calculation using Stokes theorem if we consider the inner surface as a surface bounded by this loop. So this is our F, calculation of flux using surface S in the Stokes theorem. However, if we consider outer surface in the Stokes theorem, then F S prime will be, now we'll have a negative sign, curl of A, because the orientation of surface S prime is along the inward perpendicular to this spherical surface, dot ds over the surface S prime, and this will be equal to minus mu naught upon 4 pi G by R square, and the angle which is subtended on this complementary surface will simply be 4 pi minus omega, where omega is the angle subtended on S, times R square. This will be the area of the surface S prime. R square will cancel R square. So now we'll have F S prime equal to minus mu naught G 4 pi minus omega divided by 4 pi. So if we do calculation using surface S, then we find that probability at point n is proportional to 1 plus cos of phi, where phi has contribution due to kinetic energy term as well as magnetic field, and magnetic field contribution we are calculating using the surface S. So this will be 2 pi L2 minus L1 divided by lambda dB plus Fs prime Q times Fs prime, Q times Fs, because we are using the surface S, Q times mu naught g omega upon 4 pi, and we also have a factor of h bar because this was Q times F divided by h bar. So Q times Fs is mu naught g omega upon 4 pi, and we have a factor of h bar. So this is for the calculation of F using surface S. We get probability is proportional to this. But if we calculate F, if we do calculation of F using surface S prime, then we find that probability is 1 plus proportional to 1 plus cos of, this term remains the same, 2 pi L2 minus L1 by lambda dB plus, here we have Q times Fs prime. Fs prime has a negative sign, so we have a negative sign here, minus 1. Fs prime is minus mu naught g 4 pi minus omega and divided by 4 pi, and we also have a factor of h bar. So these are two different expressions for probability that we get using two different surfaces S and S prime in the Stokes theorem. However, in the experiment we must of course get the same result no matter which surface we use in our calculation. The result must be same for the interference pattern. So the difference between these two phase differences, this phase difference and this phase difference, must be an integral multiple of 2 pi. So we get Q mu naught g omega divided by 4 pi h bar minus, we already have a minus sign here, so this becomes plus Q mu naught g 4 pi minus omega divided by 4 pi h bar. This must be equal to 2 pi n for some integer n. So if we simplify it, then this thing cancels with this minus term here, so we'll get Q times mu naught g divided by h bar equals 2 pi n, or Qg divided by 2 pi h bar mu naught, also mu naught Qg divided by 2 pi h bar must be equal to an integer. So this is the condition, consistency condition that we get because our answer for the probability must be same independent of which surface we use in the Stokes theorem. Now this condition shows that if we have a magnetic monopole of value g, of magnetic charge g, then the product of electric charges and the charge of the magnetic monopole must be quantized with these additional factors mu naught divided by 2 pi h bar. This is known as Dirac quantization condition. Dirac quantization condition. So this is simply a condition of quantization of electric charges if there is any magnetic monopole present in the universe. So more precise definition is of course that the product of the magnetic charge and any electric charge in the universe must follow this equation, where n could be any integer.